Okay, all right, so we're recording now. All right, so the last announcements I have should give you all the changes. Essentially, it boils down to, if I took the test, I would not have gotten 100%. Okay, I probably may have gotten, I don't know, 95% or something like that. So what I basically did was I scored out of 95 because I didn't do that well. I didn't get 100. I would not have gotten that. Okay, so I sort of graded with 95 being the top, and that being the case, you sort of got 5 extra points unless that puts you over 100. If you got over 100, you only got 100. Okay, some of you did that, which essentially means some of you are better students than I am a teacher. Okay, so that's the way that worked. But yeah, if you join late, go ahead and just put it in the chat, and that should not be.
It says something like we have 2 scores. We've got our gross score and like adjusted score. So
the adjusted score is the score that I actually keep. That one is 5 points higher. That's the one that actually goes in my grade book.
Okay, understood.
Yeah,
5 points higher and it's out of 100, or is it 5 points higher and it's out of 95?
It's out of 100.
Okay.
So everything's out of 100. The short of it is everybody got 5 points because I would not have gotten 100 on the test based on my answer key that I botched so many times. Okay, so the easiest way to say it is the higher score is the one that goes in my grade book. Okay, and for everybody that's 5 points higher, unless that puts you over 100, sorry, you don't get over 100, you only get 100. I mean, you folks don't need the extra points anyway. Okay, so that's the way that worked.
Understood, thank you.
All right, yeah. Any other questions about that quickly on the test? And looking ahead, I'm probably thinking all the remaining exams, or be ready for the possibility that all remaining exams are going to be the entire time. So you get the entire class period for exams 3, 4, and 5, because some problems are just really long. In fact, this last test, question number 7, was already fairly long, unless you realize how to do a shortcut to find the normal vector that I mentioned. You could multiply by a scalar multiple to make things a little bit easier. Okay, so be that as it may, we'll see how it goes. So let me share the screen now. So if I go back to this little calendar, you might think that we're sort of way ahead. In some sense we are, I suppose, because where are we? We are here now. Okay, and now that we've caught up all of this, my original plan for 14.5 and 14.6 wasn't going to be until the 11th of March. But again, don't forget, I have to catch up a day somewhere here. So we're not as far ahead as you might think. Okay, so that being the case, I'm likely to move up the exam date, which was originally scheduled for the 23rd. I'll let you know. Maybe a good time is the Thursday before that. That would be the 18th, I suppose. So we'll see how it goes. Okay, so not set in stone yet. We'll see how it goes. But I'm definitely ahead now. Okay, so that being the case, I'm going to aim for 14.5 and maybe some of 14.6. If I don't get to that, that's okay. And more than likely, we'll finish a little early today because of that fact that I'm sort of ahead. Okay, every time I say I'm sort of ahead, I'm a little bit leery of saying that because I never know if I'm going to get sick or, my internet goes down. Like last semester, I was down from the internet for a whole week, so I had to catch up for a whole week. But, we'll see how it goes. All right. Okay, so game plan is 14.5, some of 14.6. In case you're wondering, I'm not going to give you a quiz today. It's too much to give you a quiz and a test on the same week, but I will likely give you a quiz next Thursday. Everybody remember, next Tuesday is a flex day. It's a holiday for you folks. So no city college classes. Teachers are supposed to meet and do stuff, but students don't have to do stuff. So after today, our next class meeting will be on the 4th, and I'll likely give you a quiz on 14.5 and 14.6, or whatever I cover today. I guess is the easiest way to say it. I haven't decided what's going to be on yet, but I don't think I need to. And again, since quizzes are so low pressure, open book, open note, open discussion, I don't think I need to worry too much about that part of it. Okay, and let me check the chat. So okay, difficulty joining. Okay, so yeah. Okay, so I think we're back where we are. All right, so just know that for future exams, I might let you have the entire class period of 2 hours, and we'll see how that goes. Okay, so 14.5 now. Let me give you key formulas to put on your cheat sheet and so on. We're now doing the multivariable form of the chain rule. Okay, so on page 937, here's one variation of the chain rule from Calc 1, right? The Leibniz notation. dy dt is dy dx, dx dt. It kind of looks like you can cancel out the dx's, right? So to find a derivative with respect to t, you find a derivative with respect to x and multiply it by the derivative of x with respect to t. That was one variation of the chain rule. Okay, so in multivariable calculus, same thing, same concept of getting things to quote unquote cancel out. Okay, so again, using the Leibniz notation, page 938. So here's one version that you can have. Okay, dz dt, box 2, the partial of f with respect to x times dx dt, plus the partial of f with respect to y, dy dt. Okay. Again, the funny backwards 6 is for multivariable. Okay, it's the partial with respect to x, and then dx dt, that's the regular one variable, x is a function of t. Again, it kind of looks like if you want the rate of change of z or f with respect to t, you kind of chain these together. It kind of looks like the x's cancel out. It kind of looks like the y's cancel out. So if I were to make you memorize it, which I'm not, that's one way to memorize it and say, oh, okay, I want the rate of change of the function with respect to t. I line it up like so. So the dx's cancel out and the dy's cancel out, quote unquote. Okay, so dz dt, box 2, page 938, put that on your next cheat sheet. Partial of f with respect to x, dx dt, plus partial of f with respect to y, dy dt. Okay, now another variation of the same formula is down here. Okay, but lest you get confused, this is the same thing as this. Instead of putting f here and here, they put z, but otherwise it's the same thing. Okay, so dz dt, rate of change of d with respect to time, partial of z with respect to x, dx dt, partial of z with respect to y, dy dt. Again, the nice thing about the Leibniz notation is it kind of looks like you can cancel out the dx's and dy's. So this is the same thing as this, except instead of putting f, it's z. It's completely identical. So do you want to write it twice? It's up to you. You just know that z and f are the same for most of our purposes, right? Z is f of x and y. Okay, I mean, it's just like in Calc 1, whenever you saw f of x, you know it meant y, right? So now whenever you see f of x and y, you know it means z. So you can say partial of f or the partial of z, it means the same thing. Okay, now it gets more complicated if instead of single variable, like dx dt and dy dt, x and y could have multiple variables also. For instance, they could have functions of s and t. So it gets more complicated. So that would lead you to this variation of the chain rule. Bottom of 939. Okay, this long thing. So z is a function of x and y, but x is also a function of two variables. Here they call it s and t. Y is also a function of two variables, s and t. So since everything here is multivariable, you don't write any d's. Now the d is proper here because this is just z is a function of t, single variable. X is a function of t, single variable. Y is a function of t, single variable. Once you get into multivariables, you have to put the funny backwards 6. Partial z with respect to x, with respect to y. In this case, everything is multivariable. So it says z is a function of x and y are functions of s and t. So you have two flavors, two varieties of it. Okay, so put this on your next cheat sheet. Okay, and yes, I don't think it's really that hard. It's just long and tedious sometimes. Okay, so the partial of z with respect to s is the partial of z with respect to x times the partial of x with respect to s. Again, it kind of looks like the dx's cancel out. Plus partial of z with respect to y, partial of y with respect to s. Again, it looks like the partial with respect to y cancels out. This is exactly the same thing, except you're taking the partial of z with respect to t. So partial of z with respect to x, partial of x with respect to t, partial of z with respect to y, partial of y with respect to t. Okay, so in my opinion, it's not that hard, it's just long. Okay, and one thing you will note, it looks like for any one problem you have to do 1, 2, 3, 4, 5, 6, 7, 8 derivatives, but actually you don't. You quote unquote only have to do 6, because notice this is the same as this. Okay, and I don't know if I can. No, sorry, I can't do it with 2 different pens. But anyway, that one is the same as that one. So when you get to doing this, you just copy this one. And similarly, what else matches is partial of z with respect to y comes here. So even though when you do problems of this type, there are 1, 2, 3, 4, 5, 6, 7, 8 derivatives. Okay, so even though there's one problem, there's 8 derivatives involved, right? But you're really only doing 6, because once you get this one, copy that answer and put it there. And once you do this one, copy that answer and put it there. Okay. And as you might guess, this is only a function of 2 variables. If you have a function of 3 variables, it gets a lot longer, as you might guess. Okay, there's some problems like that, not too many. The book doesn't give us too many, and I don't give you too many. Now, I have to give you some. You kind of have to get the feel of how bad it is to have 3 variables involved. But, you know, I don't want to give you too many of those. Right. Which is here. This is the so-called general version. I don't think you have to look at this, really, in my opinion. It's on page 940. So the general version is correct. That's what you do if you have a function of many variables. If you have a function of n variables, okay, then you just link all n of them. Okay, so I don't think it's worth having that, okay, but it is worth showing you at least one of the 3 variable type. Yeah, I think I'll show you this type. Okay, W is a function of 4 variables, f of x, y, z, and t. Okay, and that's commonly the case if you go to the 4th dimension. Sometimes people say time is the 4th dimension, f of x, y, z, t. But x, y, z, and t are all functions of 2 other letters, u and v. Okay, and they made a little tree diagram here, okay, where W has 4 variables, x, y, z, and t, and x, y, z, and t all are functions of u and v, u and v, u and v, u. Okay, so this long mess here, partial of W with respect to u, partial of W with respect to v. So partial of W with respect to x, partial of x with respect to u. Can't even say it. And again, it kind of looks like the partial with respect to x cancels out. Then do the same thing for y. Partial of W with respect to y, partial of y with respect to u. Then do the same thing for z. Partial of W with respect to z, partial of z with respect to u. And finally, partial of W with respect to t, partial of t with respect to u. Now, what is this? Partial of W with respect to v. Okay, and I don't want to say the whole thing all over again because it's long. In writing it out, all that happens, these u's get changed to v. See that? That's v, that's v, that's v, that's v. Everything else is the same. So if you actually had to do this problem, this is the same as this, so you just do a copy job. That's the same as that, so that would be a copy job. That's the same as that, so that's a copy job. And that's the same as that, so that would also be a copy job. Okay, so there's that. All right. Implicit differentiation. Okay, it's on page 942. So here's one that you want. They go through a mini derivation of it over here. You can look at it or not. I'll just give you the result. Okay, so you have y as a function of x. Okay, and so you have capital F of xy equals 0, defined implicitly. Then dy dx is negative I think I like writing it this way. Negative fx over fy. Partial of f with respect to x divided by partial of f with respect to y. Okay, in this form, you have to have the function capital F of x, y, all on one side and 0 on the other. Okay. Now remember in Calc 1, you did some implicit differentiation, right? And that was still correct. Here's another way to do implicit differentiation in terms of doing multivariable calculus. Okay, so you get the same answer. So dy dx is negative fx over fy. The caveat is that you have to have capital F of xy all on one side set equal to 0. And then the multivariable case, box 7, page 943. So what's happening now is you have capital F of x, y, and z is equal to 0. So function of 3 variables equal to 0. So you pretend z is a function defined implicitly. Capital F of xy, f of xy equals 0. Okay, there's a derivation. You can look at it or not. Okay, here's the result. So put this on your cheat sheet. Partial of z with respect to x is negative. Okay, I like to write fx over fz. And partial of z with respect to y is negative fy over fz. Okay, maybe I'll just write that in my book since I know I'm not reselling my book or anything. So it's a little bit more compact. Okay, how's that? Okay, so the partial of z with respect to x is negative fx over fz. Partial of z with respect to y is equal to negative fy over fz. And once again, you're not really taking 4 derivatives because fz is repeated. So once you find the partial of f with respect to z, just copy that answer and put it over there. Okay. All right, so we're going to do some of this stuff. Okay, so use the chain rule to find the corresponding derivatives. Okay, so 14.5. One to 11, 21 to 35 odd. Okay. So for those of you that don't have the book and aren't getting it, page 943. Okay, there's 1 through 4, 5 through 8. Okay, next page. 9, 10, 11, 12, 13, 14, 15. That. 21, 22, 23, 24. Okay. And let's see, that's up to 33. Was 33 my last one? 35. Oh, was it 33 or 35? Let's take a look. 5. Okay. And some of these are really long, unfortunately. Okay, so again, I don't think they're hard, but just long. Okay, 14.5, page 943. Number 1, z is equal to xy cubed minus x squared y. X is t squared plus 1, y is t squared minus 1. Okay, so z is a function of 2 variables. X is a function of 1 variable, y is a function of 1 variable. That means I can use this form. dz dt is the partial of z with respect to x times dx dt. Okay, so again, when you just have a single variable, function of a single variable, you can use the d, like Calc 1. Once you have more than 1 variable, 2 or more, then you use the funny backwards 6, partial notation. So partial of z with respect to x dx dt plus partial of z with respect to y dy dt. Okay, so you're just doing a bunch of derivatives. Okay, so the partial of z with respect to x differentiate with respect to x, that's going to be y cubed minus 2xy. Okay, so that's that part. And then dx dt, that's easy, 2t. Plus partial of z with respect to y, derivative with respect to y, 3xy squared minus x squared, okay, times dy dt, also 2t. And you can leave it like that. You could do more algebra, but don't feel like it. Okay, so that's essentially it. Okay, 5 asks for dw dt, where w is a function of 3 variables. Okay, so there's the 3 variable case, and x, y, and z are all functions of 1 variable. Okay, so x e to the y z, again, I think it's easier at the appropriate time to think of it as x e to the y z to the negative 1, right? To avoid using the quotient rule. Y over z means y z to negative 1. All right, so by formula, except we have one more case. This is the 2 variable case. 3 variable, just add the next variable. So dw dt is a partial of w with respect to x times dx dt. You can line it up, it looks like the dx's cancel. Partial of w with respect to y, dy dt. Partial, when I say partial, it means partial derivative, but that takes too long to say. So partial of w with respect to z, dz dt. Okay. So here we go. Partial of w with respect to x. Well, that means all of this is constant, e to the yz. Times dx dt is 2t. Plus partial of w with respect to y. So that means x is constant, z to negative 1 is constant. So the derivative is going to be the same thing, x e to the y over z. And then by the chain rule, times the derivative of y z to negative 1 with respect to y. Well, that's going to be z to the negative 1. So z goes down there. So x over z e to the y over z. And then multiplied by dy dt. Dy dt is just negative 1. See? So you just have to be careful about your derivatives. So, and partial of w with respect to z. So derivative of x e to the y over z is x e to the y over z times the derivative of y z to the negative 1 with respect to z. That would be negative y z to the negative 2. So there's an extra negative y z to negative 2 means put z squared in the bottom. And then multiplied by dz dt, that's easy, that's just 2. Okay, so again, it's really just remembering your rules of derivatives and just being careful that you know how to do your partial derivatives, hopefully. Okay, 9, a little bit more stuff. Z is equal to natural log of 3x plus 2y. X is s sine of t, y equals t cosine of s. So z is a function of 2 variables. X and y are both functions of 2 variables, also s and t. So this time, you want the partial of z with respect to s. That's the partial of z with respect to x times partial of x with respect to s. It's hard to say this stuff, but notice it looks like the partial with respect to x cancels out. So you have the partial of z with respect to s, at least this component, and then there's a y component. Partial of z with respect to y times partial of y with respect to s. Again, it looks like these cancel out, so you just add up partial of z with respect to s, sort of. Okay, partial of z with respect to x. 1 over 3x plus 2y times the derivative of the inside with respect to x, that's 3. And then times the partial of x with respect to s. What's the derivative with respect to s? Just drop the s, sine t. All right, plus partial of z with respect to y. So again, it's going to be 1 over 3x plus 2y times the derivative of the inside with respect to y. That's going to be 2. And then partial of y with respect to s, partial with respect to s, going to be negative t sine of s. So there's a negative, there's a t sine s. Okay, and then since they had a common denominator, I decided to just put them together. So best final answer, 3 sine t minus 2t sine s all over 3x plus 2y. Let me raise it up for you a little bit. Okay, do the same thing for partial of z with respect to t. Okay, we already did that. So we just copy it, 3 over 3x plus 2y. We already did that, partial of z with respect to y. Just copy that, 2 over 3x plus 2y. So I just need the partial of x with respect to t, derivative with respect to t, s cosine t. And then I need over here, we copy that, partial of y with respect to t, cosine s. And once again, you have a common denominator. So 3s cosine t plus 2 cosine s over 3x plus 2y. Okay, so that's that. All right, that's that type of problem. And now, just like in Calc 1, you want to find specific values of derivatives. So let me show you line 21. Find the derivatives, and then they tell you to plug in. S is 4, t is 2, u is 1. Okay, just like in Calc 1, right? Calc 1, f of x equals, I don't know, sine x minus ln x plus square root of x squared plus 1 or whatever. Find the derivative. Okay, and then afterwards, find the derivative at x equals 5 or something like that, right? So same thing here. Find these partial derivatives and then plug in s is 4, t is 2, u is 1, whatever the case may be. Okay. So here's how these work. Z is equal to x to the 4th plus x squared y. X is s plus 2t minus u. Y is stu squared. Okay. They give me s, t, and u. Now, my derivatives are going to have x and y also. There's going to be x's and y's all over here. And s's, and t's, and u's. There aren't going to be any z's. Okay. Just like think of Calc 1, when you're first doing y equals f of x and you were doing derivatives, you never plugged in for y, right? In fact, you didn't plug in for y until implicit differentiation, maybe. Okay, so same thing here. You will have to plug in for x and y, so that's why we have to figure them out. So how do you do that? Simple, just plug in. So x is s plus 2t minus u, just plug these guys in. So 4 plus 2 times 2, 4, minus 1, 7. So x is 7. Y is stu squared. So s is 4 times t is 2 times u squared is 1. So 4 times 2 times 1 squared is 8. Okay. So when I do my derivatives, my expressions will have s, t, u, x, and y. So I just plug in 4, 2, 1, 7, and 8. That's all. Okay, so partial of z with respect to s, we use the chain rule. Partial of z with respect to x, partial of x with respect to s. And again, you know you change it right if these kind of look like they cancel out, right? See the partial with respect to x cancels out here. And same thing here for y. You kind of want the y's to cancel out. So partial of z with respect to y times partial of y with respect to s. So again, it kind of looks like these would cancel out. So you have two components of the partial of z with respect to s. All right. So here we go. Partial of z with respect to x. Partial of z with respect to x. 4x cubed plus 2xy. Times partial of x with respect to s. Partial of x with respect to s is 1. Plus partial of z with respect to y. partial of z with respect to y, that's nothing. That's x squared. And then partial of y with respect to s. Partial of y with respect to s, just drop the s, tu squared. Now I just plug in, right? 4x cubed plus 2xy times 1 plus x squared times tu squared. So x is 7, x is 7, y is 8, x is 7, t is 2, u is 1. Plug everything in, take my word for it, 1582. Maybe you don't want to take my word for it, but I actually looked in the back of the book for the answers for most of these because I don't always trust myself, as you know. That's it. Okay. Now, partial of z with respect to t, change that s to a t, change that s to a t. Partial of z with respect to u, change that to u, change that to u. Everything else stays the same. So here's the formula for partial of z with respect to t. Partial of z with respect to s, that's still 4x cubed plus 2y. Just copy that over here, copy that over here. Likewise, partial of z with respect to y, we already did that, didn't we? What did it come out to be? X squared. Just copy that, x squared, copy that, x squared. Okay. Then these are new. Partial of x with respect to t. Partial of x with respect to t, 2. Okay, and then we already did that. Partial of y with respect to t. Partial of y with respect to t, just drop the t, su squared. Okay. And then just plug everything in. 4 times 7 cubed, x is 7. 2xy, 2 times 7 times 8. Multiply all that by 2. Plus 7 squared, x squared, su squared, 4 times 1 squared. I did it before, 3164. Okay. Partial of z with respect to u. Yeah, you just copy all this, change s and t to u, change s and t to u. So partial of z with respect to x, we already got that, just copy it for x cubed plus 2xy. Partial of x with respect to u, partial of x with respect to u, -1. Plus partial of z with respect to y, we already did that back up here. We did that way back here. It came out to be x squared. Just copy it. And then times the partial of y with respect to u. Partial of y with respect to u, 2 stu. Okay. And once again, plug in. 4 times x is 7, 7 cubed, plus 2xy, 2 times 7 times 8. All of that times -1. Plus x squared is 7 squared times 2 times s, which is 4. T, which is 2. U equals 1. Grind that all out. -700. Okay. And then 25 gets, kind of clumsy. N equals p plus q over p plus r. Okay, so n is a function of 3 variables, and p is a function of 3 variables. So is q, so is r. So you have a lot going on here. Okay. So n is p plus q over p plus r. When it's advantageous to do so, I think of it as p plus q times p plus r to the -1. And here are all the relations. Okay, they said u is 2, v is 3, w is 4. I forgot to show you that. So u is 2, v is 3, w is 4. take all these, plug it in here, and here, and here to find the corresponding p-values. You plug stuff in. So let's see. P is U plus VW. So that's 2 plus 3 times 4, 2 times 12 is 14. Q is V plus UW. So V is 3, UW is 2 times 4 is 8, Q is 11. And R is W plus UV, 4 plus 2 times 3, 4 plus 6, 10. Okay, so at the appropriate time, I plug in U is 2, V is 3, W is 4, P is 14, Q is 11, R is 10. Okay, partial of n with respect to Q. Partial of n with respect to Q. Okay, so how do I think of it? I split this up into two fractions, P over P plus R, which is constant because I'm differentiating with respect to Q. Therefore, its derivative is 0. Plus Q over P plus R. Think of that as having coefficient 1 over P plus R. It's 1 over P plus R constant times Q. Therefore, the derivative is 1 over P plus R. And then I plug in P plus R, comes out to be 1 over 24, evidently. 1 over P plus R. Let's see, 1 over 14 plus 10, right? Okay, partial of n with respect to R. Partial of n with respect to R. That's a little bit harder. So think of it as P plus Q times P plus R to the negative 1. This becomes like a coefficient. So you just copy it, P plus Q. And then differentiate with respect to R. So negative 1 comes down. I'll have P plus R to the negative 2. Negative 1, P plus R to negative 2 times the derivative of the inside with respect to R, but that's just 1. Okay, clean it up. Negative P plus Q over P plus R squared. Plug in. Okay, so P plus Q is 14 plus 11, which is 25, divided by P plus R squared. P plus R is 14 plus 10, so 24 squared, so negative 25 over 576. Okay, so if you're careful with the derivatives, I think you can get it. It just, like I say, it can get really long. Okay, partial of P with respect to U, I also need. So partial of P with respect to U, 1. Partial of Q with respect to U. Partial Q with respect to U is W, and that's 4. Partial of R with respect to U, V. And what's V? 3. Plug everything in. So I guess you just have to take my word for it. But plug in P and Q. This is negative 1 over 576, it looks like, times 1, plus 1 over 24 times 4, plus negative 25 over 576 times 3. Okay, just take out the parts and put them together. Comes out to be 5 over 144. So just plug everything in. Okay, what time is it? We'll go a little bit longer. Partial of n with respect to V. Whoops, back up here. So there it is, partial of n with respect to P, partial of P with respect to V, partial of n with respect to Q, partial of Q with respect to V. It takes a long time just to say it. Partial of n with respect to R, partial of R with respect to V. Now, we already have the partial of V with respect to V, that's W, which is 4. We have the partial of Q with respect to V, that's 1. And we already have the partial of R with respect to V, that's 2. It's U. Right, so I just plug everything in. So that was -1 over 576 times 4 plus 1 over 24 times 1 plus -25 over 576 times 2. Yeah, I know the calculations are pretty messy. Okay, grind it out, -5 over 96. And finally, one more like this. Partial of n with respect to w, partial of n with respect to p, partial of p with respect to w, plus partial of n with respect to q, partial of q with respect to w, plus partial of n with respect to r, partial of r with respect to w. Okay, partial of p with respect to w. V, which they gave me was 3. Partial of q with respect to w. U, which I now know is 2. Partial of r with respect to w. 1. Throw everything in. Okay, partial of n with respect to p, we already did that before. -1 over 556 times that thing, 3, plus 1 over 24, we already did that before also. Partial of n with respect to q. Bring back over here. Then partial of q with respect to w, 2. Plus partial of n with respect to r, partial of r with respect to w. -25 over 576. That's just a copy job, essentially. That showed up in all of them. Right, -25 over 576, -25 over 576. Just copy them. And then what else? Partial of r with respect to w. That's 1. Okay, I cleaned up the arithmetic, ended up with 5 over 144. Okay, so you can take my word for it or not. Figure it out on your own. That's that. Okay, and yeah, let me run through a focus job for you again, in case you couldn't see it that well. Here, here. Okay, and then back up top here. A little bit more, more. And you can see that a lot of these are very long. Very long to do some of these. Okay, I think that pretty much does it. All right, I think it's a good time to break. So I haven't quite finished 14.5. I'll probably finish it after break and sneak in some of 14.6. Okay. All right, so let me check the chat. Is there anything new in the chat? No, I guess not. Okay, about 6:55-ish, about 7:10. Start up again about 7:10. I'll put that in the chat also. Okay, folks, I'm going to pick up where we were. I was really not going to go that much longer, to be honest with you. We are a little bit ahead, so I'll just try to keep, quote unquote, a little bit ahead. And then we'll just go from there. Okay, so I had some problems at the end to do involving the implicit differentiation. So the 27, 29, 31, and 33 type. Okay, so I'll just do one of each of those types, and that pretty much should be it, I think. Okay, so 27, the directions are find dy dx using equation 6. That was the equation that we saw a while back. So the thing you want to do is put everything on one side first, equal to 0. So when it says y cosine x equals x squared plus y squared, call f of x y x squared plus y squared minus y cosine x, and that's equal to 0. I could move that over on that side. That also works. But this way I just have to move one item. Okay, so by formula, dy dx is negative fx over fy. Okay, so what's the partial with respect to x? 2x plus nothing. And the derivative of negative y cosine x with respect to x is positive y sine x, because the derivative of cosine is negative sine, right? And divided by the partial with respect to y. Nothing. 2y minus cosine x. So there we go. Here's dy dx. And incidentally, a side note, you might remember you could have done this using implicit differentiation back in Calc 1, right? So you could do that. You'll see you get the same answer. Okay, then 31, you have a function of 3 variables. Okay, so find a partial of z with respect to x and a partial of z with respect to y. Okay, so 31, I'll do x squared plus 2y squared plus 3z squared equals 1. All right, move the 1 over. So f of x, y, z is x squared plus 2y squared plus 3z squared minus 1 equals 0. Okay, so by formula, partial of z with respect to x is negative fx over fz. It's pretty easy. So the partial with respect to x is 2x, divided by the partial with respect to z is 6z. So negative x over 3z. Partial of z with respect to y by formula is negative fy over fz. Partial with respect to y, 4y. And f sub z is the same. We already did it, 6z. So negative 2y over 3z. That's all. Okay, then 35, and that's the last one for the section. So the temperature at a point xy is T of xy measured in degrees Celsius. A bug crawls so that its position after T seconds is given by x equals radical 1 plus T, y equals 2 plus 1/3 T. X and y are measured in centimeters. The temperature function satisfies T sub x of 2, 3 is 4. T sub y, 2, 3 equals 3. Okay, the rate of change of temperature in the x direction at the point 2, 3 is 4. The rate of change of the temperature in the y direction at 2, 3 is 3. How fast is the temperature rising on the bug's path after 3 seconds? Okay, so we're given all of this information. At t equals 3, we're at the point 2, 3. Okay, so x is 3, x is 2, y is 3. T sub x at 2, 3 is 4. T sub y at 2, 3 is 3. So use this version of the chain root, the partial of t with respect to t. I know that sounds funny, but capital T is temperature, little t is time. rate of change of temperature with respect to time. That makes sense, right? As time goes by, temperature changes. So by formula, partial of t with respect to x times partial of x with respect to, dx dt, plus partial of t with respect to y, dy dt. Again, the regular d's, if it's a function of one variable, function of one variable, function of one variable. The backward 6, if you have more than one variable. Okay, so partial of t with respect to x times dx dt. So dx dt, where'd it go? So that's, pretend that's 1 plus t to the half. So 1/2, 1 plus t to the negative half, or 1/2 radical 1 plus t. Then I plug in t equals 3. So it's 1/2 times square root of 4 is 2, 1/4. And what is dy dt? 1/3. Okay, that's it. I just plug everything in, then I'm done. So partial of t, big T with respect to little t. Okay, so partial of t with respect to x, they told me that's 4, times dx dt at the given point is 1/4. So 4 times 1/4, plus partial of t with respect to y at that point, they told me it's 3, times dy dt, 1/3. So that's 1 plus 1. So final answer is 2 degrees centigrade per second. So 2 degrees Celsius per second is my answer. And that's pretty much it for that. All right, let me just aim it a little bit better for focusing purposes. Raise up my paper. Hopefully you can see all that. All right, so mark off 14.5. So I'll do introduction of 14.6, do a quote unquote few problems with it, but I can do more next time. And then we'll call it a day. How's that? Okay. So I'm actually done with 14.5. So yes, I'll go ahead with 14.6. Everybody remember that Tuesday is a flex day, no class again until next Thursday. Okay, so in terms of quiz, I'll probably ask you something from 14.5. I know they can get real long, okay, to find all these derivatives. So I'll keep that in mind when I'm giving you the quiz. That I want to give you enough so you can get the feel of all the multiple derivatives going on, but I don't want to make it too long that it just gets, really long. Okay, so introduction of 14.6. So what's the concept for 14.6? Okay, so we now have something called the directional derivative. So this is nice. A big advantage of multivariable calculus. Directional derivatives, and something called the gradient. So I'll definitely give you all the formulas you need that you want to put down on your cheat sheet. Okay, and maybe I'll do a few problems and then that's about it. Okay, directional derivative. Calc 1, you pretty much just have dy dx, rate of change of y in the x direction. Okay. Now we can have the rate of change with respect to x in the x direction. Okay, so if I think in the xy plane, rate of change of a function with respect to x, you're going specifically this direction, right? Rate of change of a function with respect to y, you're going specifically that direction. Well, what if I want the rate of change going that way, or that way, or that way, or that way, or that way, right? So you can find a rate of change in any direction. Okay. And think of it being on a hill or on a hillside. The best thing I can show you temporarily, something like this. Imagine you're walking on a mound or a hill like this, right? Or, you've walked in hilly, grassy areas, right? You say, well, how steep is it? Well, it makes a difference if you're walking this way or this way or this way or this way or this way, right? Some ways the slope might be 0. If you walk another way, it's pretty steep up. If you go another way, it's steep down, right? Imagine you're standing right here, right? Okay. Say, how steep is it? Well, which way are you going? Am I going that way or that way or that way, right? Okay. And likewise, you could have the rate of change in 3 variables. If you have x, y, and z, you could have a rate of change with respect to x in the positive x direction. You can have the rate of change of a function with respect to y in the y direction. You can have the rate of change with respect to z in the z direction. Okay, maybe if I take out the clutter, the 3 vectors look like that. I, j, and k direction, right? But maybe you want to go that way, or 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 that way, right? You can go any which way. So rate of change of the function in that direction, or that direction, or this direction, or this direction, or whatever, right? So you have a much more rich number of possibilities compared to Calc 1. And now when you're in Calc 1, you just think, oh, dy dx, that is so ordinary now, right? Rate of change of y with respect to x. But now you can say, is that all? That's the only thing that there is? You can go any direction, rate of change with respect to whatever direction you want. Okay, so we now know rate of change with respect to x in the x direction. And by the way, you can also go negative x in negative x direction. It would be the opposite, as you might guess. Rate of change in the y direction, you can have the rate of change in the negative y direction, and rate of change in the z direction, rate of change of z in the negative z direction. But you can go that way or whatever. So how do I find the rate of change in any direction? And we do want to keep one convention here. Okay, if I talk about the rate of change with respect to x, y, and z, those are all unit vectors. Okay, so back in Calc 1, when I did dy dx, which was actually a limiting version of delta y over delta x, right? So suppose it came out to be 5. It's 5 over 1, right? Then we're saying, as I move x one direction, y moves up 5. That's usually how we think of it, right? Okay. So to be consistent, for all the directions that we're going to go, they're always going to be unit vectors. So if they don't give me a unit vector, first thing you have to remember to do is change it to a unit vector. Okay, rate of change in that direction, but in that direction, it's got to be a unit vector. Okay, because if I make it a much bigger vector, then of course you're expecting a much larger rate of change. So to be consistent with everything we've done before, like dy dx, rate of change of x is 1. Or even when I did partial of z with respect to x and partial of z with respect to y, that's as we change x by 1 unit, how does z change? As we change y by 1 unit, how does z change? So now we want to go in any direction. So if they give us any direction, make it a unit vector. So the convention is to have a unit vector. Okay. Here's the formal definition of a directional derivative. You don't have to write it down. I'm not making you memorize it, but it does look something like the limit definition of a derivative, right? What they're trying to show over here is, rate of change of temperature. It depends on which way you're going, right? So let's see. I think this is I'm pretty sure it's a temperature thing. Yeah, these are sometimes called isotherms, I believe. Okay, I think these are meant to be isotherms, meaning same temperature. So if I walk along that line, it's the same temperature. And then if I go this way, the temperature changes. Okay, so you can say the rate of change of temperature in that direction is 0 and that direction is 0. But if I go this way, maybe it's increasing by 5 degrees per unit. And if I go that way, it gets colder or whatever, right? Right, so here's a formal definition of directional derivative. You don't really have to worry about it, okay, because there aren't any homework problems involving it. But please notice in the definition, it's in terms of a unit vector. The directional derivative in the direction of a unit vector, 2-dimensional, A, B. Okay, and here's the notation. So we will use this notation. We're almost never going to use this definition. Okay, but DUF at x0, y0, or sometimes don't put the x0, y0. So D for derivative of f in the direction of u. So we've had the rate of change with respect to x, partial with respect to x. You're going in the x direction, rate of change in the y direction. Now I want to go some other direction. So derivative of f in the direction of u. What if I want to go that way or that way or that way? What's the rate of change? So d, u, f, derivative of f in the direction of a unit vector u. we're not just going in the X, Y, or Z direction. We're going any direction that we want. Okay? And you can see it's a much more rich possibility, right? If you're standing on this mound, okay, so how steep is it? It depends which way you go. Some directions, the slope is 0. In some way you're going down, and some others are going steep down. Another direction you're going up and steeper up, right? Imagine you're standing on this hillside, okay? And you can just turn your body, say, okay, if I go that way, right, I'm going up. If I go that way, I'm going level. If I go this way, I'm going down. If I go this way, I'm going much steeper down. If I go that way, I'm going a little bit up, and so on, right? So you know that when you're standing here, depending on which way you go, you're either going to go up or down. So you want to, what's the rate of change if I go this way or this way or this way or this way or whatever. Okay. So, you know, that opens up a much more rich variety of possibilities than just now seemingly very ordinary Calc 1, you know, dy dx. You know, it's almost like, is that all? That's all we had. Rate of change of y only in the x direction. Okay, now we can go a whole bunch of directions. All right, so 948, this is what you want on your cheat sheet. Okay, although this is the 2-dimensional version, you might want to think of the 3-dimensional version later, because once you have the 3-dimensional version, right, you just cover up the last one to get the 2-dimensional version. But anyway, this is what you're generally going to use. Okay, so page 948. If f is a differentiable function of x and y, f has directional derivative in a direction of any unit vector u. Okay, please notice that it's got to be a unit vector. Okay, so if they say in such and such a direction, okay, the question might trick you. They give you a direction, but it's not a unit vector. You first have to change it to a unit vector, and you know how to do that. Okay, so it's fx a plus fyb, where a and b are the components of the unit vector. So duf at xy is fx at xy of a plus fy xy b. Now, when I write it, I get lazy, but it's faster. I sometimes leave off the xy. Okay, just write duf is fx a plus fyb. A and b are the components of the unit vector. Okay, can you guess the 3-dimensional flavor? What would you add? Let's see, there's fx and fy. There's the fz. And they got fxa, fyb plus fzc, where c is the z component, as you might guess. And that's the 3-dimensional flavor. And let me see if I can find that for you quickly. Where's the 3-dimensional flavor of that? It's here somewhere. Can't seem to find it offhand, sorry. Well, anyway, my advice is to just go ahead and put it here. So go ahead and write this down and put what? FZC. Okay, maybe I'll just pause it. Plus FZ at XYC. That's if you're doing the 3-dimensional flavor. So this is a 2-dimensional flavor. For 3D, just put FZ at XYC. So to save space on your cheat sheet, just put this one down. And then you know if it's 2-dimensional, just lose that one and you have that. Okay. All right. Definition of something called a gradient vector. Gradient vector. Okay. How do you write it? Grad F or del F, sort of like the upside down delta symbol. Okay, so grad F or del F. Okay, it's basically the vector where the components are the partial derivatives. Okay. So 2-dimensional flavor of the gradient vector. Page 950, so put this on your cheat sheet. The gradient of F. So we will write either grad f, G-R-A-D-F, or del f, the upside down triangle. Okay, it's a vector. It's basically fx, fy, or partial of f with respect to xi plus partial of f with respect to yj. Again, I think it's better for you to put the three-dimensional flavor, put the partial of f with respect to zk. And that's a three-dimensional formula for the gradient. Okay, with that notation for the gradient, we can actually now write this also. So you might want to write this. I'll put this from time to time. So the derivative of f in the direction of u of xy is del f dot u. You can kind of think of it as a dot product, okay, where it's fx times a plus fy b and then plus fz c. Okay, so this is sometimes useful. It's a dot product. See, this kind of looks like a dot product, right? You have fx, fy, fz dot a, b, c. So you take the first components fx times a plus fy times b plus fc times c. Okay, so again, for the gradient, put this down. It's a vector. The vector whose components are fx, fy, and the three-dimensional one fz. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Gradient vector. Okay. All right, and three-dimensional definition of the directional derivative. You don't have to worry about it, but again, it kind of looks like the Calc 1 definition of derivative, right? And yeah, they do have the three-dimensional gradient right here, number 13. Del f is fx, fy, fz, or partial of f with respect to xi, plus partial of f with respect to yj, plus partial of f with respect to zk. So again, thinking of a dot product, equation 14, duf, derivative of f in the direction of u, of xyz, is del f dot u. So you take the dot product of fx, fy, fz with the components of the unit vector a, b, c. 14 there. Okay. So again, this gradient vector, the components are just the partial derivatives. Okay. It's just fx, fy, and fz. Okay. So the directional derivative, take that gradient vector and dot it with the unit vector in the direction that you want to go. Okay, then a theorem of maximizing the directional derivative. You can put this on your cheat sheet. There's a lot to it, but if you get the hang of it, you kind of get it. It's on page 952. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative duf of x is, okay, what is this thing when they write it like that? Gradient vector, I was going to say, what's the gradient vector? It's a vector. Therefore, this is magnitude of the gradient vector. And it occurs when u has the same direction as the gradient vector del f of x. Okay, so you're standing on this hillside. Oh, where's that hill? Right? And you know, when you're standing here, you can go that way, that way, that way, which will give me the maximum rate of change. Okay. So do I go that way or that way or that way or whatever, right? Where can I find the maximum rate of change? This theorem says the maximum value is the magnitude of the gradient vector, and the direction is the same direction as the gradient vector. Okay, so which way do I go? You find the gradient vector, that tells you which way, and the magnitude of the gradient vector is that maximum value of the directional derivative. Okay, they got a little mini proof here that we know that duf is del f dot u. Okay, and from a long time ago, this can be written as magnitude of del f, magnitude of u cosine of theta. The magnitude of u is 1. So del F cosine theta. When is this maximized? Well, that's maximized when the cosine of theta is 1. Okay, that occurs when theta is 0. Okay, the angle between del F and U. So the biggest this can ever be is when cosine of theta is 1, right? Be stuff between -1 and 1. Okay, and the angle between them is 0, then that means the maximum value occurs when you're in the exact same direction as the direction of the gradient vector. Okay, so you can put this on your cheat sheet. All right, that's a lot of stuff. You know. Okay, and maybe one more. Tangent planes to level surfaces. It's sort of a variation of a formula we had before. Okay, so here's a tangent plane with the equation f of x, y, z is equal to k. X, y, and z are functions of t. F of x, y, z is k. Here it is. Okay, so you may want to put down 19. The tangent plane to the level surface f of x, y, z equals k. Tangent plane. Okay, so fx, x minus x0, plus fy, y minus y0, plus fz, z minus z0 equals 0. Okay, so 19 is worth having. 20 is worth having. Okay, the normal line looks like we have symmetric equations, right? So that's x minus x0 over fx equals y minus y0 over fy equals z minus z0 over fz. Notice I got lazy and didn't say x0, y0, z0. You don't actually have to say it, but you do have to plug in. Okay, when you see all this stuff, it means plug in the values. So they'll tell me this is 3, this is -6, this is 1, or whatever. Just plug them all in. Okay, so 19 and 20. Okay. All right, I think I'll do just very little of this and then we'll call it a night. How's that? Okay, so 14.6, just give you a feel of it. We can do more next time. 5 to 25 odd, 33, 41 to 45 odd. Okay. Let me just get our feet wet with some of the problems. Okay, find the directional derivative of f at the given point in the direction indicated by the angle theta. Okay. So number 5, f of xy is y cosine xy 0, 1. Now they only give me the x and the y, but you can always figure out the z by plugging in. Theta is pi over 4, 45 degrees. Okay, so notice what's happening now. Okay, this is a 3-dimensional graph. Okay, it looks like some surface, whatever. Okay, it's a function. It passes the vertical line test. Okay, you start off with a point on the floor. Any point on the floor, you go up, it's only going to hit 1 point. It's defined by this. You want to go in the 45-degree direction. What is the rate of change, right? So it's very rich variety of directions. You can see what's happening here in this picture. You can have rate of change in a whole bunch of directions, I guess, right? So once you have that, dy dx that you had in Calc 1 looks very ordinary. Rate of change of y with respect to x, and that's it. Right? All right, first I need a unit vector, pi over 4. Okay, if I'm going in the direction of 45 degrees, then you know that this is radical 2 over 2. This is radical 2 over 2 from Calc, a trig, right? 1, 45 degrees, radical 2 over 2, radical 2 over 2. So a unit vector in the direction that I want is radical 2 over 2, radical 2 over 2. So that's my A and B. All right, so that doesn't look like it. Maybe I'll make it look a little bit more like that. Radical 2 over 2. Okay, so du of f, the derivative of f in the direction of u, a very specific direction, 45 degrees in standard position. So del f dot u. So del f is fx, fy. So partial with respect to x. So that'll be negative y sine xy times the derivative of xy with respect to x, that was y. So this is negative y times y sine of xy. Comes out to be negative y squared sine of xy. Then partial with respect to y, looks like I got to do a product rule. So first times derivative of the second plus the second times derivative of the first. Okay, well, the second times derivative of first is easy. That's cosine of xy. Okay, how about first function times derivative of the second? Let's see. So I have y, then negative sine of xy. Looks like there should be a y here. Sorry. Goofed again. Y times negative sine of xy times the derivative of xy with respect to y. That's an extra x. Okay, so I think that's right now. So cosine xy minus xy sine of xy. Okay, so now I plug in 0 and 1. So plug in 0 there, sine of 0 is 0. That wipes that all out. That's nice. Plug in 0 and 1 here. Let's see. If I plug in 0 here, that's gone. If I put 0 and 1 here, 0 times 1 is 0. Cosine of 0 is 1. Okay, so the derivative of f in the direction of u. So dot product of f and u. Okay, so it's 0, 1, that's the gradient vector, dot with radical 2 over 2, radical 2 over 2. Unit vector, gradient. Okay, 0 times radical 2 over 2 is 0. 1 times radical 2 over 2 is radical 2 over 2. So that's the answer right there. Show that to you a little bit more here. All right, so one more time. First, you find the gradient vector. Okay, what's the gradient vector? It's the vector whose components are fx and fy. And if you have a three-dimensional case, you have the third component being fz. And you dot it with the unit vector. Notice they didn't give me the unit vector. I had to figure it out. But that's easy. You did 45 degrees, radical 2 over 2, radical 2 over 2. Okay, so the gradient vector came out to be 0, 1 at the point 0, 1. So in general, this was fx and fy, but I plugged in the 0 and a 1. Fortunately, they came out very nice. And so I have the vector 0, 1 dot radical 2 over 2, radical 2 over 2, comes out to be radical 2 over 2. Okay, bottom line, for this function, whatever it looks like in space, at the point x equals 0, y is 1, and z is, I'll just figure it out, z is 1, right? It's 1 times cosine of 0, it's 1. So in space, at the point 0, 1, 1, specifically in this direction, radical 2 over 2, radical 2 over 2, what's the rate of change of that unit vector? Square root of 2 over 2. That's what it means. Okay. I will show you 9 and then I'm going to quit. I'll call it a night unless you have questions about anything. Okay, 9 is a three-dimensional version. Okay, f of x, y, z is x squared yz minus x, y, z cubed. The point is 2, negative 1, 1. The unit vector is 0, 4/5, negative 3/5. Find the gradient of f. So by definition, gradient is the vector whose components are the partial with respect to x, y, and z. Evaluate at a given point, just plug it in. And find the rate of change of f at p in the direction of the vector u. Okay. So that's that. So I'll be done with this in a couple minutes. So if you want to ask questions, you can either unmute yourself at that time or put it in the chat. Otherwise, we'll just call it a night. Okay, f of x, y, z is x squared yz minus x, y, z cubed. Here's the point. There's a unit vector. Okay, quick double check. If you square each of these, 0 squared is 0. 4/5 squared is 16 over 25. Negative 3/5 squared is 9 over 25. 16 over 25 plus 9 over 25 is 1. Okay, square root of 1 is 1. So it is indeed a unit vector. Its magnitude is 1. Okay. So you can see what's happening. We're getting a rate of change in a different direction, not just the rate of change of y with respect to x in Calc 1, which is now quite ordinary. We can go that way or that way or that way or whatever way. Okay, so gradient vector, del f, or sometimes grad f, G-R-A-D, is fx, fy, fz. So derivative with respect to x is 2xyz minus, drop the x, yz cubed. Derivative with respect to y, let's see, just drop the y, x squared z, minus, drop the y, xz cubed. That's nice. Partial with respect to z, just drop the z, so x squared y, minus, okay, that's a z cubed, so 3xyz squared, fx, fy, fz. Okay. Part B, what's the gradient vector at the given point in space, 2, -1, 1. So from the origin, you walk out 2, 1 to the left, 1 up. Okay, that's the point you are at space. What's the gradient vector there? So I just plug in 2 times -1 times 1 minus a -1 times 1 cubed. X squared is 2 squared times 1 minus 2 times 1 cubed, and 2 squared times -1 minus 3 times 2 times -1 times 1 squared. Okay, all that stuff. Okay, in any event, it comes out to be -322 if I did it right. Okay, so let's see, that's -4 minus a -1, that's -3, right? That's 4 minus 2, that's 2. And this is -4 plus 6, so 2. Okay, so the gradient vector at that particular point is -322. So this new weird gradient vector, it's almost like a function, right? You give me a different point, on this graph, whatever this graph looks like, you have a different gradient vector. Okay, so you have this point, it's a different gradient vector. That point over there or that point down there, they have different gradient vectors. Okay. And finally, C, find the rate of change at that point in the direction of 0, 4/5, -3/5, which means you're not going anywhere in the x direction. 4/5 is a unit to the right in the y direction, and 3/5 is a unit down in the z direction. Very specific direction. Okay, so by formula, it's del f dot u. It's a dot product of the gradient vector, -322, dotted with the unit vector, 0, 4/5, -3/5. So that's easy. So -3 times 0 is 0, plus 2 times 4/5 is 8/5, plus 2 times -3/5 is -6/5. Add them all together, 2/5. Okay, what is this 2/5? For this particular graph in 3D, whatever it looks like, you can have a computer simulation for 3D, what it looks like. At one particular point, 2, -1, 1, in one particular direction, that direction, what is the rate of change of the function? 2/5. Okay, very powerful. Okay, so again, once you get to multivariable, a whole new world of possibilities opens up for stuff, much more compared to what you did in Calc 1. Okay, all right, so I think I've accomplished what I wanted to accomplish. 14.5 and quote unquote sum of 14.6, not quite half, but I gave you the introduction stuff, so maybe I'm half in terms of what I need to do. Okay, so no class on Tuesday. Our next class is March the 4th, and I'll go on with 14.6 and maybe some of 14.7. I'll likely give you a quiz on 14.5 material. Okay, all right, so that's it for now, folks. So if anybody has any questions about anything, you can put it in the chat or unmute yourselves, otherwise we'll quit. Okay, so I'll wait for a moment. Anybody have any questions? Or okay, I don't hear anything and I don't see anything in the chat, so let's call it an evening. All right, okay, have a good night, everybody, and no school Tuesday. I'll see you again next Thursday. All right, okay, good night, everybody.
Thank
Bye.
you.
See you.
Thank you.
Okay.
Thank you, Professor.
Good night.
All right.
Good night, everybody.